The Matsuda identification method is based upon continued fractions. Consequently, you should learn something about them first. A continued fraction is a fraction which has many nested levels, like this. A continued fraction is obtained from two sequences. One of them is the sequence with the numbers that appear here in the denominator. The other is the sequence of the numbers that appear here in the numerator. To this sequence, I usually add this integer part here as term A0. Now, just as from only one sequence, for instance this one, I can obtain a series by summing all its terms. From these two sequences, I can obtain a continued fraction by these successive sums and divisions. Because this nested notation is not very practical, two other ways of writing a continued fraction can be found in the literature. The most compact notation is the Plingsheim notation. I put here the integer part, and then I simply notate here the sequence in the numerator and the sequence in the denominator. Here I put this dumb index showing how far the summations and divisions go. If there are infinite levels, then this upper limit here will be plus infinity. Another possibility is the Abramovitz notation. It is more similar to this nested notation, but I will simply write A0 plus B1 divided by A1 plus, and then the fraction that should go here comes out, and I will put it here. This doesn't mean that I'm multiplying these fractions, of course. It is all that follows that should go here, and then all that follows, all this, that should go here, and so on and so forth. Given a series, a summation with an infinite number of terms, we can truncate it, summing only a finite number of terms. And this summation may provide us a good approximation of the value of the entire series of the infinite summation. Likewise, given a continued fraction with an infinite number of nested fractions, we can truncate it and sum and divide only up to a certain finite number of terms, and the result may provide us with a good approximation of the value of the continued fraction. Let us see an example with a real number. Suppose that we want to find a continued fraction for pi. Truncating the corresponding continued fraction will give us a fraction which is a good approximation of pi. Now, as we know, pi is equal to 3.14159 and so on and so forth. This is sufficient. The integer part is 3, so we can write that pi is equal to 3 plus pi minus 3, which is the same as 3 plus 1 divided by 1 divided by pi minus 3. That will be 0.14159 and so on and so forth. Now we can calculate this, and the result is 7.0625 and so on and so forth. So we can again separate this into an integer and a fractional part. We will have here 7 plus 1 divided by 1 divided by 0.0625 and so on and so forth. And since this fraction here turns out to be 15.996 and so on, we can again write this as 3 plus 1 divided by 7 plus 1 divided by 15 plus, well, you got the idea. In this way, we can get a continued fraction to represent pi. Now, truncating this continued fraction will provide us a fraction which is an approximation of pi. The first two values we get are 3 plus 1 divided by 7 and 3 plus 1 divided by 7 plus 1 divided by 15. Now this, 3 times 7, 21, so we'll have 22 sevenths. Here we will have to calculate 3 plus 1 divided now 7 times 15. This gives 105, so it's 106 divided by 15. And the result will be 3 plus 15 divided by 106. And this gives 318, so 333 over 106. This turns out to be 3.1429, not a bad approximation of pi for such a simple fraction, and this turns out to be 3.1415 and so on and so forth, so we'll have 4 decimal positions correct with this fraction. The annoying thing with these approximations is that we have to begin in the innermost fraction and then calculate outwards. However, there is a better way of carrying out these calculations, which allows us to first find an approximation and then improve it with each new added fraction at a deeper nested level. Let's see how we can do that. Suppose that we have a continued fraction and we want to know the value it takes when we truncate it after a certain number of terms. That is to say, we want to know this after n terms. Rather than calculating it from the innermost fraction and then working outwards, we can simply calculate the following sequences. And then the ratio pk divided by qk will give us an approximation of this continued fraction after k terms. Notice that because these sequences are found recursively, we do not have to go back to the beginning to find the next approximation. We keep on finding new terms and finding better and better approximations. Proving this is rather straightforward. Notice that the first approximation we can find is this. Now, what is P1 divided by Q1? Here we have P of 0, which is a 0. Here we have P of minus 1, which is 1. So it's just B1 here. Now we divide by, this is Q0, that's 1, so it's quite all right like this. Q of minus 1 is 0, so this term is actually not there. We will be left with, which is exactly what we wanted. Now we will prove that if this is the exact approximation of order k, then adding another term, we will get the approximation of order k plus 1. Now, suppose that this is true for a certain order, and we already saw that it is true for the very first approximation. What will happen with the next? What does it mean to add another term to our approximation? It means, for instance, that if I only got as far as this, I will now add to a1 b2 divided by a2. If I had got as far as this, I would now add to a2 a new term, b3 over a3. If I had got as far as this, I would add to a3 a new term, b4 divided by a4, and so on and so forth. Consequently, here, this new approximation will be ak plus bk plus 1 divided by ak plus 1. This will be our new value because I increased one level downwards. The same goes here, of course. No change is needed in bk, so we are left with the following. Now, when we look carefully, we see that ak pk minus 1 plus bk pk minus 2 is precisely our definition of pk. So all this is pk. And what we have here in the denominator, ak minus 1, bk, k minus 2, is what we defined as qk. So this here is qk. And now we see that the expression we have here is this, but this has been increased from k to k plus 1. Look, ak, here we have ak plus 1. Pk minus 1, here we have pk. bk, bk plus 1. pk minus 2, pk minus 1. And the same goes in the denominator. Consequently, we showed that if this is true for level k, then it will also be true for level k plus 1. And we know that it is true for level 1. So consequently, being true for level 1, it must be true for level 2. Being true for level 2, it will be true for level 3, and so on and so forth. This is how a proof by mathematical induction proceeds.